So last day we have discussed about various types of triggers and also coincidence. This is your first class. So you can look into the video, also the class notes of your fellow students. Fine. So what I was saying is, we talked about trigger and coincidence, right? Now today we are going to basically discuss some practical examples, some more practical examples of trigger, how it is achieved in an experiment. Okay, now what you see over here is basically a two-body reaction. Projectile A falling on target, and as a result a nuclear reaction is happening where this is a light particle small b which is emitted, and then a nucleus is emitted. Oh sorry, this is B, right? So this is a basically two-body nuclear reaction. Why two-body? Since only two bodies are produced as a final product and then they are moving out. Okay. Now you can think of such very basic type of reactions like elastic scattering, electron-electron scattering, something like that. In that case, both will be the same species. Now, first of all, we are talking about very simple case, two-body scattering. So, how to achieve that? First, what we will do, this is the target, that is capital A, and this is the projectile small a, right? So, small a is coming, then interacting with the target over here, and this entire thing happens inside a chamber. Yes, yes, I am coming. And this whole thing, even the beam which enters over here, the whole thing happens, actually the whole thing happens inside a chamber which is in vacuum, because if this happens in your air, this projectile will interact with the air molecules and the reaction will happen just over there. We will not be able to make the fusion of these two, okay, small a and capital A. So we have to get rid of the air molecules, and for that we have to use a beam pipe, something like this, where this is kept in vacuum, okay, using vacuum pump, and basically this is your target chamber. This stuff is your target chamber where actual this experiment is occurring. So this is the real life scenario of this basic diagram, how it is implemented in your daily actual life. These are important. I will later on show you actual experimental diagrams showing the setup, how it is implemented. Okay, so now coming back to this. So after the reaction, the two species are produced, small b and capital B. Now they can be emitted in variety of angles. Okay, they can be emitted over here, 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 here. Variety of possibilities are there. Variety of possibilities. Now, what we want to do is we want to study one such possibility. Now, what we will do? Since we have got two outgoing particles over here, we are going to use two detectors. One detector, say, let me name the detectors. Name the detectors. Suppose this is your detector X. This detector X is used to detect the particle B. Okay, and then next I am using detector Y, which is used to detect this big capital letter particle. Okay, this one. This particle I am using detector Y, and this particle, for this I am using detector X. So effectively I am using here two detectors. Okay, fine. Now the thing is that, so what should be the trigger that as a result of this reaction, so suppose there is this small a forming one capital A, and then one such possibility, small b and corresponding capital B is detected in this detector X and this detector Y. Okay, so what should be the trigger? The trigger should be just your X dot Y, isn't it? That should be the basic trigger. Basic trigger means we will detect only the counts in X and Y when both are present at a time. Then those counts will correspond to this coincidence when this particular reaction happens. Okay. Now, what about something else? Say for example, look over here. This reaction A plus A forming B plus B. Right? This is the reaction. Right. Now suppose in this detector X, I am getting some count, okay, at a time, but at that time I am not getting any count in detector Y. Can you explain what does this mean? This means that now suppose I am saying that this detector capital X is sensitive to this capital B and this detector capital Y is sensitive to this capital B nucleus and this one is sensitive to small b nucleus. This means this detector X will not detect the capital B nucleus and this detector Y will not detect the small b nucleus. Okay. Now at one time I am getting some counts in this capital X but I am not getting any counts over here. What does that mean? This simply means that there can be situations where in this detector capital B enters but its corresponding coincident is emitted in some other angle where we do not have the detector. That's why in this detector Y I am not getting any count. This is a possibility, it can happen. We will be able to detect only those events where both of them enter at the same time. Okay? So you have to understand this thing. In real experiment, there can be so many possibilities. One be entering here, another corresponding coincident be going in this direction. But I do not have any detector. So I will not be able to detect this event. I will be only interested out of so many possibilities, only that possibility coincidence event I will be detecting where one B will be entering in X and corresponding capital B will be entering in Y, and this is what is shown. And the meaning of this thing X dot Y as trigger simply means that we detect only when there are counts in both of them, not when there is count in only one. Because if there is count in only one, the corresponding B other nucleus I don't know where it is. What's its energy, what's its angle, we do not know. That we will not be able to detect. You understand? There are so many coincidence possibilities, out of which only this particular coincidence possibility I am choosing. You can think of it like that. Say for example, these are the two possibilities. Okay. So suppose at any time there can be possibilities like this. This one for small b, this one for capital B. They can be emitted like this, like this, like this, like this. There are so many possibilities. There are so many. But since we have detectors here and here, only this possibility out of all of them we will be able to detect. This is clear. Okay. Now,
sir, detection at the
English. Yes.
Just at the restriction থাকবে না যে কারণে momentum conserve করতে হবে ওই জন্য বলছি।
What momentum? It is always being conserved in this reaction. Otherwise, the reaction will not happen. When you are coming to the university, there are so many buildings out there. Why are you entering this particular lab? It is just like that. And your friend, he is also entering this particular lab. So both of you are entering this particular lab. But students of other advanced classes, they are entering at the same time. You are entering nuclear physics lab the other guys are entering, say, astrophysics or laser physics lab. Something like this. Why does it bother? Okay, all of them are entering the university at the same time, and then there is a bunching. Something like this. Okay.
Sir, when A goes through the S2 and it interact with the
I have still not introduced S1, S2. I will be introducing. Now, so till now, the trigger is just X dot Y. Okay. Now you see the real problem is in actual experiment what happens is that this we want to get rid of what? Accidental coincidences. This small a can hit some other beam pipe during incoming, some part of it, and then there is scattering. Okay, some beam pipe, then there is scattering in the target, and then we can get events as that. But this will be reduced, some other event, because there is already scattering going on over here. So this is not the genuine event. Such events can happen. There is a possibility that instead of coming in the straight path, some events they scatter of the beam pipe and then enter the target, and you are getting those counts in your detectors. X and Y. This is a possibility. We have to get rid of that possibility. So what do we do? So basically I want to get rid of this path. Okay, I want to ensure that it is only this straight path where the projectile is coming. So what I am doing next is I am putting two beam defining counters. These are basically beam defining counters. They are basically transmission type detectors, very thin detectors, where we have put them very small cross section, thin detectors, we have put them just into the beam. Now, then there is electrical signal from both of them. So next what I am going to do, my trigger will be now, my new trigger will be S1 dot S2 dot X dot Y. That is, I will detect only the counts when there is count in S1, S2, X and Y. What does this mean? Because the projectile is first entering in S1, then it is hitting S2, then the reaction is happening. So this is a genuine case. Suppose the projectile scatters of some other place and then enters this, then this part we will be able to get rid of using this condition, because this projectile will not trigger over here. Okay. So using two beam defining counters, I am able to get rid of accidental coincidences due to the projectile. Okay. So basically this is to reduce accidental coincidence related to projectile scattering of your say beam pipe or some other component.
Sir, are these beam defining counters like collimators?
Huh?
Beam defining counters,
Very thin transmission type.
like they are only allowing the straight beams.
You
to
know
pass.
how much thick is beam? What do you think? This is a chalk. Let me show you. Okay, so see the thickness of the chalk. Okay, how much thick is the beam, do you think? Give me your pen. Actually, in real life experiments, beam is just, you are seeing this dot over here. Okay, very small. Maybe the diameter is 1 to 2 millimeters, something like this. So much thin we are talking about. And for that purpose, this chalk itself, the cross section is good enough. So the beam defining counter, it might be of this much cross section that you are saying. So you need not take a very big one. You understand? Suppose I use such a big one, but this is useless. We don't need that. In real experiments, the beam are very small. Now think of the engineering feat. The beam has to travel from such a long distance, maybe 100 meters from where it is produced. Then that pinpointed point, it has to come hit the target and okay, how much cross overall structure is the target? The target is not very large. Maybe where should I use? The target is effectively this much, only this much. So something coming to hit over here, say for example, at a distance of say 100 meter. Can you imagine? So you have to use quadrupole magnet and other magnet to steer the beam so that it enters over here. Now how do you know that the beam will just fall over here? You have to put at various junctions in the path of the beam, you have to put such beam defining counters and you have to keep on checking the coincidence. Okay, I am getting the signal. So the beam is over here. Now you have to change it. Okay. So this is how, this is known as beam tuning. This is an important topic in accelerator physics. This is not a part of experimental nuclear physics. The beam tuning is basically a part of accelerator physics. But this is again important because otherwise you will not be able to do any nuclear physics experiment. So just imagine how much engineering feat. There is right now not much physics, basically engineering. Think of it. The beam hitting over here from 100 meter. Such an important engineering feat. Okay. Now any more questions? So basically I am telling you the importance of the beam defining counter over here. Next problem, accidental coincidences. This is your pen. Okay. Now accidental coincidences can happen from over here. So I have got rid of this possibility using the beam defining counter. Next, you see this projectile hitting the target. Now there are many types of nuclear physics experiments. Okay, one is your transmission type experiment. Transmission type experiment where we have got a thin target. Thin target. The target itself, this A, is very thin, so that when A enters, it also exists. Only a small part of A actually undergoes the reaction. This is basically thin target experiment. Thin target experiment. Okay, such type of experiment can happen. Then in this case, this projectile after exiting your target, this has to be stopped. It cannot keep on going every long distance because you see, this entire thing has to be put inside vacuum, isn't it? So it costs a lot of money even to create vacuum. So what we do, we put something called beam dump. Beam dump. Dump the beam. So when the beam goes something over here, some material will be there, the beam will just hit it and it will be stopped. So you can say it's a very thick material where the beam will be stopped. Okay? So here also, if this is a thin target experiment, then this beam after exiting the target, it will be entering a beam dump. See, beam dump. Okay, now let me remove these parts. Okay. Fine. Now this we understand as this is detector Y, this is detector X, where it is detecting A, and this one is this is detecting B, and this one is detecting capital B, BPH. Okay. Now something dangerous is going to happen. What I tell you right now is that all the beam will be coming and will be stopped in this beam dump. Okay, what do you think? There will be no reaction. Think of it, a train comes and hits something. What do you think will happen? Huge collision. There will be some huge noise, some material going out, something like that. Now here, think of it, the projectile has got very high energy. This is a nuclear particle. Okay, so maybe some sort of elastic, inelastic reactions will happen. So scattering plus reaction will happen in this beam down. What will be the result? The result will be there will be particles, even gamma rays, exiting everywhere from this beam down. Now these particles can enter your detector X and can enter your detector Y. This is real life experiment. Things do happen. Now the question is, how are we going to get rid of these particles? So we have to add something over here as well. So this time what we are going to do is the following. So see, if this is the beam down, say this is the beam down BD, then I am going to put a detector directly over here, and let me name this detector Z. Okay, so this is your detector Z directly on the body of the beam down. So if this is the beam down, say if this is the beam down, then on the body of the beam down I am putting your detector Z on the body where the beam comes and hits. And then what will happen, I will put a condition over here, S1 dot S2 dot X dot Y dot Z bar. That is, I will count when there is signal over here, signal over here, signal over here and no signal from here. Because if there is signal from here, then this means there is some scattering entering my detector, which I don't want. So I want to get rid of it. So see, out of so many possibilities, I want this count, I want this count. So yes, I want again this count, I want this count. Yes, but I don't want count from here. That's why I have used a bar. So this is your trigger. See, this is the trigger, Z bar, and this Z bar is basically to reduce accidental coincidences from events happening in beam down. So these are due to accidental coincidence related to your projectile, and this is for accidental coincidences for events happening in beam down. So this means the real reaction happens over here, and to reduce events which come before it, I am using this two beam defining counter, and again to reduce events which come from outside sources like beam down, I have to use a detector Z. Okay, so this is a basic example. Till now we are just talking about simple two-body scattering, how trigger is experimentally implemented. So you expect this question in your examination. Write it down. Briefly discuss about the implementation of trigger in a two-body scattering, explaining the logical reasons behind each element. Explaining the logical reason behind each element of the trigger system. Yes, one thing I forgot to tell you is this. Look here, there are two types of nuclear physics experiment is happening. First is your thin target experiment. Another, what is happening in beam down. This is something what is known as thick target experiment. So both are happening together. Here the beam is being transmitted in the thin target, but here the beam is entirely deposited. So thick target means the beam will be deposited. In actual thick target experiments, what happens is that In actual thick target experiment, the beam falls on capital A, so this is small a, falls on capital A and it is entirely stopped. So this is your thick target experiment. Okay. Now tell me what is the difference between thick target and thin target? Where do you think you will get this capital B? You will not get this normally if the energy is small, then small b and capital B will be produced and they will be just at rest. They will, after formation, they will be coming into rest in the target itself. They will not be moving out. You understand what is happening in the thick target experiment? But if my target is thin, if it is very thin, my target, then after formation, this B can be emitted from the target, small b and capital B, and then I can study them. So for studying them, I need thin targets. Okay. Now previous day I talked about compound nuclear reactions. They can happen in both thin target as well as thick target. Okay. We can have compound nuclear reactions in both thin as well as thick targets.